of this bijection being defined from the other direction is k times continuous.
K times continuous the differential.
Differential, sorry.
Basically, what it says is that if a map is defined in a neighborhood of a point and the Jacobian is non-degenerate at that point, then there exists a neighborhood where it is invertible, like this bijection. But it's only local.
So if Q0, of course, is this map applied to P0, it's saying that if this is k times continuous, k times differentiable, continuously differentiable here, then we can define the inverse map of this. It's bijective, we can define an inverse, and this will be k times differentiable. Does that make sense? Does that not make sense? No. Okay. So anyway, I believe his use of this is to prove the implicit function theorem, which is slightly more general, and we don't have time for it. There's a class here in a few minutes. But the implicit function theorem is the same condition. If the Jacobian is invertible around a point here.
You need to describe, to set it up what the implicit function theorem says.
Okay.
It's a different map.
Right. Okay. So we'll try and write this down as quickly as possible.
You still have 15 minutes. So we have enough time.
Okay. So this is, again, a theorem. If suppose you use a neighborhood around a point x0, which is an RK. V is a neighborhood of Z0, where Z0 is an RL. And we have a map. We have a map defined by U cross V into RL. So this is a map that takes, the cross product of these two vector spaces. So it takes an element of one and the other into RL. And we assume that this F is also k times differentiable. We then also assume.
So RKs have to be different?
I'm sorry?
Because you have RK and CK?
Yeah, that could be M or something.
Right, he uses the same notation, but yeah, I don't think there's any need for them to be the same. Right, so we assume that the derivative, the Jacobian again, with respect to Z, I guess, of this map, is invertible.
Well, you need to understand that this is square matrix. It's a L by L matrix. That's why he introduces K and L split and into.
Right, because the mapping itself.
Otherwise, it would be a rectangular matrix.
Right, the mapping itself is not necessarily square. But if we take the Jacobian of just the space RL, then it is a square Jacobian. Right? I mean, is that kind of clear? Is this visible at all to you guys? Or like if I write down here?
Barely. Next line will not be.
Okay. So we'll assume that that's invertible. And then this is what we get for that. Right. We say, okay, U naught is this function applied at x naught, z naught. And I also have a little bit of bad notation here, which is the Jacobian evaluated at these points. So again, these points are the centers of these neighborhoods that we're discussing here. So the Jacobian evaluated at that point of this space, we say that it's equal to some value. The function is equal to some value. Then this equation can be solved in some sense or rearranged in such a way that it defines z as some map of x.
Well, that's a different F.
Right.
Oh, it's E.
So, sure, phi. It defines, right, we can solve this equation in some sense for the z variable. We can rearrange it, and that's the use of this, right, for x. And then this phi is also a CK map. So the point, the sort of motivation of all of this is that if we have some vector valued map, and we know that its Jacobian is invertible around a point, then we can sort of solve for some of these variables in terms of the other. It's a very general statement and is used in geometry quite a lot, from what I remember. And he uses this to discuss a lot of the things about this system of ordinary differential equations. So
basically, you have L equations for L variables z. So these are L equations for L variables, and it basically tells you when this is solvable. If the Jacobian here by dz is invertible, then it is solved. It doesn't mean that you can find that function, but you know that it exists. It is defined in the neighborhood of that point. That's all it says. So just write down nonlinear equation, L of them.